right, so welcome back. Last week we started talking about lists and list-based data structures. And we started out by doing a full demonstration for an array-based list that will hold integers. And we went through quite a bit, so I just want to use our maybe 5 minutes up here at the start to review what we did. So remember that we created this class called myIntegerArrayList. Remember that we are online, so if you have any questions, go ahead and post to Piazza or to the YouTube live stream. I'll see either one. We created this list, basically a list-based data structure that used an array under the hood, right? MyIntegerArrayList. Right? We started out with a block size of 10, but then we parameterized that. When you initially create this list, you create an array that can hold up to 10 integers. But you keep the size separate because you haven't actually put 10 integers into this array. We then implemented various methods, for example, add something to the end, add element to the start. And then we collapsed those all into one function that did all of that work, right? That given a particular index, you want to insert this element, it took care of everything. It took care of error checking, right? So if you gave it indices that were out of bounds, it threw this exception. If the array was already full and you wanted to add one more thing, then it made another array that was of size 10, additional 10, a capacity of an additional 10 elements. Then we made sure to make room for that element. If you were adding it right in the middle, then that means that you had to shift everything down in order to make room for it and put that element right in there, right? And then, of course, you need to do your own bookkeeping because the size of the array is not the size of the list. That's just the capacity of the list. And that's all internal. We needed to increment the size here. We also implemented methods to get an element at a particular index. Well, that's just in terms of the underlying array. Remove an element at the particular index. And when you remove this element in the middle, right, you need to shift everything down to make room for it. And that's what we implemented here. Okay? We also had this toString method that allowed us to actually look at the list and print it out. So now that we understand how this is working, what we then did is we went on to create a sorted integer list. A sorted integer list that the idea here is that you shouldn't be allowed to put anything in anywhere that you want it to, because if you had 10, 20, 30, 40, 50, and you wanted to insert, say, 25, right? You shouldn't be allowed to put it at the beginning and have 25, 10, 20, 30, 40, 50. That's not sorted. You shouldn't be allowed to put it at the end, 10, 20, 30, 40, 50, 25. That's not sorted either. So that's where we left it off. We were contemplating how to continue to implement this class right here, right? We still have the same exact constructor. That when you create a new list, you create an array that has a certain capacity. You record the current size because you haven't put anything in there yet as 0. Contains element here. We had a linear search algorithm that we used. And we'll come back to that in a second here. But now let's think about this. Add element at index. Right? Should you be allowed? We took out the methods that allowed you to add something to the end and allowed you to add something to the start, right? But should we said, should you be allowed to add an element at an arbitrary index? And we came up with no, because you don't want to add 25 just willy-nilly wherever you want to, right? So instead of getting rid of this method, though, what we did was we made it private. Because it's still a useful method, right? Internally to the class, if we want to put in 25, 10, 20, 30, 40, 50, 25 goes right here, right? We still want the ability to say, oh, well, it should go at index 0, 1, 2. In other words, you should shift this stuff down to make room for it and put it where it belongs. I wanted that functionality. I didn't want to, throw that functionality away, but I didn't want to advertise it to the outside world and break my encapsulation and break my abstraction. Right? So we're going to keep it, but we're going to keep it private. So that when somebody wants to add an element, they don't say where they want to add it. Oops. They don't say where they want to add it. Instead, we take care of that for them. Again, we as in the sorted list here. Right? We find the index at which it belongs, and then we simply call our private function to shift things down, increase the capacity if necessary, put it where it belongs, keep all the bookkeeping for us. Right? And that's our only public method here. Okay? Well, what about get element at an index? Sure, you can get an element. You're not going to remove it or anything like that. Well, you can also remove the element of the index. We'll take care of that for you. It's still sorted, right? If you have 10, 20, 30, 40, 50, and you take out 30, right? We'll shift everything down. Now it's 10, 20, 40, 50. It's still sorted, right? So that's perfectly fine. Again, to do, consider a shrink operation here. And then we have the exact same toString method here. We left off last time contemplating, well, this is a lot of repeated code, right? The toString method, the remove element at index, the get element at index. That's all the same as the other class over here. So maybe there's a way to cut down on the amount of code here. My idea was, well, maybe we should use inheritance here. Right? So let's go to the drawing board and just whiteboard this and see what it would look like. First of all, my integer list, so I'll just call it integer list, int list, versus sorted int list. What should the relationship be here? Okay. What if we used a classical inheritance and said that, well, first of all, is a list a sorted list, or is a sorted list a list? So what I mean by that is, what if I put sorted at the top, sorted list, and then a list down here as the inherited class, right? An int list and an int list. Does that make much sense? Remember, it has to follow the is a relationship. A robin is a bird, but a bird is not necessarily a robin. So, is an integer sorted list a sorted list? Is it a list? Yes, but is a list a sorted list? No. So this one seems wrong. So let's try the other one, right? In other words, the one that I originally drew over here, right? So let's go ahead and get rid of this question mark, and let's say that the inheritance looks like this, right? A sorted list does seem like an integer list. A sorted integer list does seem like an integer list to me. So let's go ahead and try to implement it that way. Let's come over here. Which class would I do this in? I would do it in the subclass, and I would say that it extends what is it called? My integer array list. There we go. Extends. Right? Nothing breaks except for, what do we have here? Before it was private, or before, when it was not a subclass, it was private. It's now complaining because it inherits that from the superclass, meaning that what? We cannot make this private. Remember the open-close principle? It should be open for extension, but closed for modification. If I remove, basically I'm removing it from the visibility. If I remove a method that is inherited from the subclass, then that subclass does not follow an is a relationship. What is an integer array list? It is a list that holds things in an array, and it also has this add element at end, add element at start, and it also has this add element at index method. Right? By making this private, I've made it so that the subclass does not have that method, or at least it's not visible. Right? It violates the open-close principle and violates the how Java works. So I'll go ahead and restore that to public, and now it will compile. But does that sound right to you? Does it sound right to have a sorted integer array list where you can go ahead and add the elements wherever they belong, but also my list dot add element at, whoops, that's not what I wanted, dot add element at the end, 25, or I don't know, 1. There we go. My list dot add element at end, add element at start, 100 or 100,000 there, right? And to arbitrarily just add any element anywhere that you want. Dot add element at index, and I'll go ahead and add, 42 to index 4 or something like that, right? Now let's print it out and see if this is indeed a sorted list. Right. Let me cut this down to only 10, maybe. There we go. There. So it was sorted before, but when we started using the interface that didn't make any sense, is it sorted now? No. So we violated one of the other solid principles. What is it? So we've got the single responsibility principle. O, open-close principle. L, Liskov substitution principle. Need to remember how to spell solid. I, the interface segregation principle, and D, the dependency inversion, right? Think of that middle one, the Liskov substitution principle. Where did that come into play? We had a shape, we had rectangle, and we had square. But squares were not always squares. They could be made into rectangles. But the type was still a square. Is it a square when it's 10 by 20? No. Is it a sorted list when you can manipulate the interface here to make it not a sorted list? No. This violates the Liskov substitution principle, right? So, is this a good idea? No, right? Don't use inheritance. What's the alternative? I really don't want to have to repeat that code. I don't want to have have this add element at index. I just want this add element, right? And get element at index, et cetera, et cetera, et cetera. I want to keep those for now. But I don't want to have to repeat myself. I don't want to copy pasta, copy pasta. What's an alternative to inheritance? Let me get rid of this. How can I reuse that functionality? An interface? So I could say that I could make it so that there's this other interface here, and I only ever treat it like a sorted list. But it's still some sort of maybe it implements a sorted list, and then I restrict that interface only to the things that add it, but not add an arbitrary index. That could be a way. That still locks me into an inheritance hierarchy of some sort, though. Right? Well, now think about your, say, I don't know, stock class or an asset class, just an asset class in general, right? Did you reinvent the wheel to make that class? What is in an asset class? It's a label. Well, what's a label? A string. Did you write your own string class? No, right? Why would you when you've got it in the standard library? You've got a purchase date. Hopefully you used a class to do that. What class should you have used? The local date class, right? Well, what's that called when one class uses another class instead of an asset? We would all agree that an asset is not a local date, right? A date is not an asset. An asset is not a date, right? We didn't lock that into an inheritance hierarchy. Instead, we used composition, right? When one class is composed of other classes, right? That's called composition. How could we utilize composition here? What if inside we owned an array list, right? List. There we go. Do I need any of this stuff anymore? Nope. Don't repeat yourself. I've already got the list, right? My sorted list will initialize that list. This dot list is equal to new, my integer list, right? Now, contains element, guess what? Oh, here. I'll leave it like this. Contains element. Now what I can do is I can define all my functions with respect to those other functions. So contains element, this dot list dot, guess what? Contains element, x. Right? Now it looks kind of weird because, well, why are you repeating this code here, right? And then this should be a return value, return, right? I'm just calling one function and that hands it off to another function, right? But at least those 10 lines of code are not repeated. I'm reusing the functionality over there, but at the same time, I'm not locked into that inheritance hierarchy. That add element at a particular index, which breaks my sorted property, right? I don't have to publish that. I don't even have to have that. I deleted it already, right? Now, this add element over here is not part of this class. So what I would do is I would need to find the index at which it belongs. So what I'll do here is I'll say to do refactor this, factor this, dot, 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 because I no longer have access to the size. I no longer have access to the underlying array, but I do have this dot list dot add element at index. If I can find the index, then I'll hand that off to the underlying list to take care of it for me. And by the way, we're following the same pattern we did here, right? What is an integer array list? It's a list that uses an array under the hood. Well, what is a sorted integer array list? It is a sorted array list that uses a unsorted list under the hood, right? So I've just got this, this wrapper, right? This onion. In the core, I've got an array. Then I wrap that around this abstraction called a list. I wrapped another layer around that called a sorted list, right? And all you have to do from the outside world, because of good abstraction, is deal with the outermost layer, right? So add element, great. What about get element at index? Again, this dot list dot get element at index, index, right? It's all just thin wrappers around what I've already implemented. This dot list dot get remove element at index, index. There we go. Takes care of it for me. There. And toString. This dot list dot toString. Just return that. Return. Turn. There we go. All right. And I think I need to return. There we go. And return. All right. Great. I've cut down on all that repeated code by simply just using a thin wrapper, right? A thin layer around this onion, right? The onion gets thicker and thicker, right? But each layer itself is a thin layer. Right? Now, how do we go about doing this? Oh, gee, I would really like to go ahead and iterate over each one of these, right? That means I would want to have, I need to know the size, right? Well, is there a list.size? I don't know. This dot list dot size? Nope, that's not public. Dot get size? I really wish there were. Well, if you wish there were, grant your own wish. What should I do? Go ahead and implement it, right? There's nothing stopping me. It's my list. I can do whatever I want. Public, int get size, right? Return this dot size. Perfectly fine to publish the size of your list, right? Okay. That takes care of that line. Okay, I want the element at the ith index because I want to compare it to x in order to know, should it go here, 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 right? 10, 20, 30, 40, 50. If you want to insert 25, 10, nope, it goes after that. 20, nope, it goes after that. 25, oh, okay, that's where it belongs, right? And all I need to do that is to be able to get the ith element. Well, guess what? This dot list dot get element at index I. Right? As long as you do it in terms of that other list, then there's really only a small amount of work that you need to extend the functionality that you've already implemented. Right? And at this point, I would point out that why do you even have your own integer list here? Just use an array list, right? And a list. But again, we're looking at how you cannot do that on the last phase of your project, by the way, right? You do have to implement it from scratch. But if I were doing this in real life, of course, I would just reuse the library. Okay? Excellent. Right. Now, let's, as a last step here, let's reflect. My integer array list, what's it good for? What can you put into this bag or into this list? Integers, right? Okay, well, what would it look like if I changed it to my double array list? Let's go ahead and copy, paste my integer array list, not 2, but my double array list. Right? Let's open that up and look and see what it would look like. Everything has already been renamed for me. But what would change? First of all, the double, right? I would have a double array here now. I would have to create a double array when I create it. Right? Does any of that stuff change? Nope. 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 What changes now? Just the parameter, right? That the outside world sees. I want to know is 3.14159 in there, right? Now, you might ask yourself, well, equals equals, there's floating point issues there. We won't worry about that right now. What about add element at index? You're not adding an integer anymore, right? You're adding a double, and that's taken care of. Get element at index. You are returning a double. Remove, you're removing a double, right? And I missed something. Double. There we go. Save that. What else? That's a double. And done. Right. What if I want this for strings? Should I cut and paste this again? What if I want this for assets? Should I cut and paste this again? No. I shouldn't have cut and pasted this to begin with. What should I have done? Don't call it a double. I want this list to be able to hold any type at all. So think about Lab 6. What did you do? You created courses that could hold students. You created courses that could hold different types of students, grad students, undergraduate students, but then you restricted it so that you couldn't hold droids or whatever it was, right? I thought it was clever. But how did you do that? You parameterized it. What is this T now? It's what? It's any type that you want, right? It's just, that's why we call it T, right? It doesn't have to be T. It could be X. But why do we use T? Because it's short for type. You could actually use type if you wanted to, but that's weird, right? Now, what is that type going to be? Any place that you put a double, you are going to replace it with a T. Now, there's a problem there that we'll come back to. Let me go ahead and rename this because it's no longer my double array list. It's going to be my array list. There we go. That takes care of that. And get rid of that double. It's no longer a double. It is a type T. There's the problem. We'll come back to that in here shortly. It's not a double. It's not a double. It is generic. T's, T's, T's everywhere. T. T. What else do you want? Return a type T. Return a type T. A local variable of type T. What is X? It's of type T, right? Etc. Right? Anywhere I replaced an int with a double or an integer with a double, I replace a T now. Now you see the power of polymorphism too coming into play. So all of the aspects of our object-oriented programming that we've covered before, abstraction, encapsulation, right? Those two came to the forefront. Then we tried inheritance, and we determined that doesn't really seem right. So we'll use composition instead. And now finally, ultimately, what we're doing is polymorphism. One type of list to rule them all. Right? Now come back over here, and let's fix this. Now the problem here is that when we were creating integers, an integer is 4 bytes. When we were creating doubles, a double is 8 bytes. Right? Those are primitive types. Do we know what we're creating here? No. We just know that these things are objects. So what we have to do, we're forced to do, and this is more of a historic reason for Java, they added generics. This was not possible in the first 5 versions of Java. They only added generics in version 6, right? 15 years ago. So what we have to do is we have to use what are called raw types. I do know that they are objects, right? And I'm going to go ahead and typecast them as whatever type you created when you created this list. All right? I'm forced to do that because Java bends over backwards to make sure that it is backwards compatible. Right? Generics were not introduced until Java 6. So the way that we deal with that internally to the class is by using raw types, these objects. And I am getting a warning here that I'm ultimately going to ignore because it says unchecked cast, right? It's a contravariance, right? Treating a bird as an ostrich, even though that's not necessarily safe. But it's safe in this case because I've parameterized the class. It's parameterized for your protection. Right? Now let's come over here to the demo, and let's rethink all of this stuff here. Okay? I want to create not an integer array list. I want to create a list that will hold anything that I want. So what did I call it? My array list. I will now parameterize it to be strings, something completely different that we haven't even used yet, right? And names, right? Equals new my array list. And now you can kind of see how the list and the array list, the actual one built into Java, has actually been built. But of course, that has a million more features and a million more methods that we're not going to get into, right? But I've repeated the core functionality here with this demonstration. Names.add. Can I add 10 to the end? Nope. Why? It was parameterized to be strings. You can only add strings. Right? I don't know if there's somebody called named 11. Or no, there is somebody named 11, right? It was on Blossom or something. Was it? outing myself as somebody who watched Blossom when I was a kid, right? There we go. It's because it came around right after the Fresh Prince. Right. There. Add name, add name, add name. Right? You can add as many strings as you want, and we can print it out here and show you that it works, right? Names dot or system dot out dot println names. Was it 11? Or somebody look that up for me and correct me if I'm wrong. You YouTubers out there, tell me what Blossom's friend's name was. Was it 11 or not? Right? There we go. I've got names here. Right? Joe instead of Chris. There we go. Right? Great. So, to recap on all of our demonstrations, right? We used abstraction to hide the details of how how internally the array grew or shrunk, right? To accommodate more elements, right? We used encapsulation to they kind of go hand in hand here, but to protect the list from arbitrary operations, I should say, right? We used inheritance at first to create a sorted list, right? Realized it was bad and instead used composition. Right? Then finally, we used parameterization, right? That is polymorphism, to have one list that can hold any type. Right? Each one of these things is basically following the principle of don't repeat yourself, DRY, right? You want as little repeated code as possible. And if you can do that through inheritance by simply just subclassing and inheriting and maybe overriding methods, great. If you have to do that through composition by creating a thin wrapper around your class, great. If you can use parameterization so that you only have to write one list to hold any type, even better, right? Ultimately, I've only made now, 100 lines of code to handle any future, and that's future-proof, right? Any new asset that you can create, I can create a list to hold those assets. Any new type that you come up with in a completely different project, of course, I could reuse this list over and over and over again, right? Okay. Any questions? Do we have the Blossom answer yet? No. Okay. Yeah, okay, there we go. You don't have the Blossom answer. Okay, go ahead. Good question. Let's find. Well, is it sorted right now? Oh, yes, it is, because C comes before J. Add elements to the end. Anita. There we go. Nope, it's not sorted. So what would we have to do to make a sorted list? Everything I did before, but I would take out the integer from this and parameterize it instead. Right? That's going a little too far. That's your responsibility on the last assignment, or not on the last assignment, but on the last phase, I should say. Right. Okay. All right. There's still a drawback here. Okay. So drawback. All right. Let's go with drawback. Drawbacks. All right. Or disadvantages. Right. Oh, sorry. Go ahead. Oh, it's 6. Okay. Thank you. Maybe that's 11 is from Seinfeld. He wanted to name his son 11. It was Mickey Mantle's number. So what? Stranger. I thought she was 1. Oh, she's 11. Okay. All right. 6 or 11, whatever. All right. So what are the drawbacks here? Well, once the capacity is reached in the array, an entirely new copy must be created. How much work goes into that? So if there are only 10 elements, of course, right? You filled it up, you create another array, you copy over of size 20, you copy over those 10 elements, right? Copy 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? Now, we're using a function to do that built into the library for arrays library for us, but ultimately it is still doing that amount of work. Copying 10 things is 10 operations. What if you had 1,000,000 elements in your array list? Now, that operation is copying 1,000,000 things. What if you had 1,000,000,000 things in your array list? Copying is now 1,000,000,000 operations, right? In other words, the number of operations or the amount of work grows linearly with respect to however many things you've got in the list, right? This operation requires n copy operations, where n is the number of elements in the list, right? If n is small, so what, right? If n is large, this becomes very expensive, right? So let's look at an alternative. The alternative is going to be a linked list, okay? Now, a linked list is different. It does not hold elements in an array, right? Instead, each element is held in a node, right? Each node has the element and a reference to the next node, right? Each node is placed in a chain, right? And linked together, right? Together. There we go. So why do you think we call it a linked list? Because they're linked together, right? So to visualize this, I'm just going to draw a pretty picture here. If you want to, you can go ahead and take a look at the other pictures on, say, the pre-prepared videos, the tutorial videos. But here's what a node looks like, right? A node is basically two things. It holds whatever data you're trying to put into it, and then it also holds a reference to another node. Well, if I've got two nodes here, and for now, let me just go ahead and put in integers, right? 10. Now, if I want another node here, I create that node, and I link it together. And that node, the first node, points to the next node. And suppose that I put 20 in there, right? I don't want to confuse you and say that this is necessarily sorted to begin with. So let me go ahead and put something else over here, 15, right? Certainly not necessarily sorted unless you make it into a sorted list, right? Now that we've got a chain here, we can start using some additional terminology. The start of the list is the head of the list, right? The end of the list is called the tail, right? So it's like an animal, or it's a snake, right? It's got a head and it's got a tail at the end. Right? How do you know that you're at the end of the list? Right? What should this point to here? Null. Here I'm going to visualize it as phi. Right? That's the universal, right? Nothing, nada, no, nothing, right? But of course, in Java, what is it going to be? It's going to be null, right? Sometimes you can actually create a this special type of node here, right? This is called a sentinel node. Sentinel. I think that's how you spell it. I'm not sure. But you can create this special sentinel node that you always put at the end so that it's not null. It's just this very special sentinel node that you can check for. Well, is the next one the sentinel node? Yes. Okay, well, then I'm at the end of the list. Here, instead, we're just going to go with null instead. Okay? So let's think through some basic operations here. First of all, what if I had this original list here? And I'll do it like this, right? Come on, copy it. Now let's go ahead and look at one operation here. What if I wanted to add 42 to the start? What would that look like? Oh no, I lost my copy paste. So I'll do this. Copy. There we go. Paste. There. Now instead of 10, of course, what is it going to be? It's going to be erase this. Be more judicious. Coloring outside the line. Sorry. That's good enough. Engineering. What's better than good? No? Good enough. All right, 42. I've created a new node that holds the element. Right? Now, how do I add it to the start? I make this thing point to the old head, and then I update my reference to the head as this node, right? In other words, if you've got a chain link, how do you add a link to one end? You just go ahead and hook it up, right? And that's your new head right there. What if you wanted to add an element to the end? Say I wanted to add 101 instead. Inside the lines, 101. And I want to add it to the end. What would that operation look like? Now, it's not like an array-based list. With an array list, you've got, say, 10 elements in there. You know where the indices are. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? You have what is called random access. If you wanted to jump to the fifth element, that's just a memory offset, right? 0, 1, 2, 3, 4 times the number of bytes each element takes, you can automatically jump there. Can you jump here into the middle of a list, on a linked list? No. What you have to do is you have to start at the head. This is not what I'm looking for. Go to the next one. This is not what I'm looking for. Go to the next one. This is not what I'm looking for. Go to the next one. This is not what I'm looking for. Well, actually, no. This is what I'm looking for because the next one is going to be the end of the list. So what do I do to add this new one? I erase that reference, link this in, and then I update this reference. Maybe it was null already to begin with, right? And now I've got this longer chain all around here, okay? What would it look like if I inserted something in the middle? I don't know what this is, but we'll just go ahead and say it's, I don't know, 20, and this one is 30, and I want to add 42, and I want to add it right here in the middle. What would that operation look like? Well, first of all, I need to create it, a node that is, right? And now how do I link that in? You can break chains, right? Chain links, you can break it and then insert a new link right in the middle just to make it longer or something like that. What would it look like? You sever that connection, right? And you make this point to the new node down here. The new node, you make that point to the old node here, and then you stretch the chain out, and it looks like that you've got right in the middle, 20, 42, 30. Right? So conceptually, I understand how to insert stuff into a linked list. Let's actually implement it. We'll worry about removing stuff, retrieving stuff, all that other extra stuff later on. Right? Let's, for now, go ahead and try to implement this in, say, Java. I will go ahead and leave the demo open here because I want to use it. But I'll go ahead and close all of my other lists here. All right. So let's go ahead and create a linked list. Class my linked list. Right. Immediately, I've learned my lesson from the first demonstration. I don't want to write a linked list for integers. I don't want to write a linked list for strings. I don't want to write a linked list for doubles. So immediately what I'm going to do is parameterize this. It is a linked list for whatever you want. Okay? All right, how do we get started here? A linked list is nothing more than a reference to the head of the list. But what is the head of the list? If I look back over here at my visualization, if I get rid of all this stuff, right, and I have an empty list, right, this is the head and the tail. And it's only one node, right? So how do you represent the head? As a node. How do you represent a node? I really wish there was a way to represent a node. Well, if you have a design wish, what do? You pull out your wand and you grant your own wish, right? So I'll pull out my wand here and let's create a node class. I'm immediately going to parameterize it here because what do I want this node to hold? Integers, doubles, strings. Which one? Yes, all of them. Right? So let's design the node class first. All right. What do you want to hold in here? Well, an element of type T, and I'll just call it item or maybe element. Right? Should I make it public? Not unless you have a really good reason to. So we'll make it private. Right? What else should I hold? What does a node look like? It has the element, right? And a reference to the next node. Next. So what is that? Also private. T. Well, now think about this. If this is a node that holds a string, right, then the next one is a string. No, the next one is another node of elements of type T. That's not recursion, right? That is composition, right? Remember that, well, you can create a local date class and then put a local date in it, right? In fact, you've done this before. Actually, no, maybe not. Say from a structure can do this as well, right? A structure is composed of other things, an integer, a double, whatever. But a structure can also be composed of another structure. That's composition, right? A student structure has a date of birth. A date of birth has integers, right? That's composition. It doesn't matter what this is. It doesn't matter if it is an instance of itself. It's not really recursion, right? It's not really self-reference. Self-reference is when you use this keyword. That's open recursion. I'm referring to myself. This is not referring to itself. It's referring to that node over there, right? And I'm literally pointing over there because that is what it literally does. It points over there. Okay. All right. Round out the design of this node. I, of course, need a constructor. So, again, I don't like to type. So, constructor using fields, right? An element next. Maybe I want to be able to create and then come back for documentation later. Maybe I want to be able to create a node without having to specify the next. Right? Maybe I want both of those constructors. For now, I'll keep it simple and just have this one constructor here. Super is implicit. Next is not going to be next because I don't want it to refer to the next, right? I want it to refer to null, right? Why do I want that? When you create a new node, where should it point to by default for the next? To phi, or in this case, null. Okay. Maybe getters and setters? Well, setters, maybe, I don't know, right? In fact, I'm going to go ahead and say, remember, you should make everything final unless there's a good reason not to, right? If you create a node and you hold that element in there, I'm never going to replace that node. I might replace what that node refers to next because I'm going to want to insert stuff at the beginning, insert stuff at the end, break the chain open and make this point to that and that point to that. So I do have an argument here for making the element final. You can't change that, but you can go ahead and change what it points to next because you want to modify your chain. Right? Okay. That means basic getters. Maybe not setters. I don't know. Let's go ahead and generate them all and look and see. Oh, good. It's seeing that the element is actually final, and it's not even giving me the option to have a setter for the for that element. So I'm going to go ahead and select all. Yeah, go ahead and do them all. All right, there we go. Maybe some other convenience functions. ... Convenience functions, convenience methods, whatever. Right. If I'm just one node, do I know that I'm the head? No, that's a function of the list. Do I know that I'm the tail? Maybe, maybe not. What do I know? I know that I have an element, and I know that I have a reference to the next element. So one question that you could ask yourself, that you could ask of a node is public Boolean has next. Right? Do you have another node after yourself? Right? Because when I described traversing this list, right? That's not what I want. Go to the next one. That's not what I want. Go to the next one. Go to the next one. Go to the next one. Right? One question you could ask yourself is, hey, you 20 node, do you have another one that I can go to? Yes, you do. Yes, I do. I'm the node now. Right? So, okay, I can go ahead and go to that. No, 101 node, do you have another one that you can go to? No. Okay, I know that I'm done now. Right? So, has next. How can I implement that? If this dot next is equal to null, then I return false. You do not have another node to go to. Else, return true. Okay. There. Has next. Right. maybe get next. I guess that was done up here, right? Okay, great. Here's an opportunity to relearn or learn if you've never seen it before, the ternary operator. Is there a better way of doing this? Let me go ahead and swap these around first of all. If it's not null, then I return true. Otherwise, I return false. Right? If it's not null, there's something being pointed to over there. There is a box over there that you can go to. So true. It's not null, so you can go to it. Having done that, if this expression is true, right, then I can just return it. Sorry, I mentioned ternary operator. This is what the ternary operator would look like, right? I'll do it that way. Return. If this is not null, then return false. True. Otherwise, question mark. Sorry, true. Otherwise, return false. And make sure that you do all of your parentheses. That's the ternary if-then-else operator, right? This is the expression. If that expression is true, then the entire expression takes on whatever this is. If this expression is false, then it takes on this value right here, right? I mean, you could do other things with it. For example, I don't know, int 42, right? Int x equals 42, right, is equal to 42, right? If x is, or not if x, but Boolean value is equal to, is x less than 42, right? Then go ahead and, not Boolean here, let's go ahead and just go with a string. I'll go yes, otherwise no. And I need to put that in that question mark, not that. There we go. There's another use of it, right? Is it strictly less than 42? Then it takes on the value, the string value, yes. Otherwise, it takes on the string value, no. Right? That's the ternary operator, but I don't even need to use the ternary operator here at all, right? If this is true, then return true. If this is false, then return false. Well, okay. Then just return the expression itself. Right? Why write many words when few words do well? Right? Okay. You can even play, if you've ever heard of it, code golf, right? You can golf, the lowest score wins. And so I can do that function in 10 lines of code. I can do that function in 5 lines of code. I can do that function in one-liner. I can do that in one line, but with fewer characters, right? And you might try to make it as short and terse as possible, right? But unfortunately, then it is no longer readable, right? So you have to have that nice Goldilocks zone, right? Not too terse, not too verbose. Now that I've got my node, and maybe I'll want to come back and redesign it a little, add features if I want to. But now I can go ahead and create my list. Private node t head. And I parameterize the node exactly the same as I would parameterize it up here. This is a linked list that holds strings. Therefore, my nodes will hold strings. Right? This is a linked list that holds integers. Therefore, my nodes will hold integers. Right? What does my constructor look like here? My linked list. Oops. This dot head is equal to, how do I know if it's an empty list or not? Well, if there's nothing in it, your head is not going to have any values stored in it, so it might as well be null. Right? Okay. Let's start implementing some functions so that we can actually look at this list, all right, and work with this list. The first one that I want is, I'll just go ahead and add a public void add element to head. Right? In other words, add it at the beginning. Right? And do I take integers, x, and I add it to the head? Nope. What do I take? Elements of type t, anything. Right? It has to match, of course, up here. Right? It can't just be, s. What is s? S is not anything that it understands because you parameterized it on t. Okay. Add element to the head. So visually, what did we do before? We had the previous head pointing here. Right? We created a new node. We made that new node point to the old head. And then we changed out the head to point to this new node. So 3 things. 1, create the new head node. 2, make the new head node point to the old head node. 3, make this list's head point to the new head node. Only 3 things. That's it. Help me write those things. Create a new node. How do you go about doing that? Node of type T. Right. Should I call it node? Should I call it new? Can't do that. New node? Or new head? Right. Whatever you want. Right. Is equal to new node of type T, also parameterized, but you don't need, you can use elision to not have to do that. What's it going to hold? X. So a new head node that holds the new element X. I'll add that to it. Right? What's wrong? You can't infer the type? Okay, fine. What? Oh, it's not visible. Okay. It's not? Huh, okay. Why did I make it private? Was that just the default? I don't think I did that. I generated that, didn't I? All right, fine. Public. And now you're happy. In fact, I think you could you can infer the type. I was going to say, well, you can infer the type. You're smart enough. Right? Me talking to a compiler. Right? There we go. New head. 2, make the new head point to the old head node. So, new head dot, that's why I created that setter. Set next to be what? This dot head. Okay. Now, what if this dot head was null? So what? Right? If it was null before and you're adding a brand new head node here, it'll still point to null after you've done this. Right? So it takes care of all the situations. Okay. Make this list head point to the new head node. This dot head is equal to new head. Done. All right. Let's play around with it over here in the demo. I want a my linked list of, say, let's keep it as integers. Right. It's harder to think about strings. List is equal to new my linked list. There we go. Come on. List dot, and the only thing I can do right now is add it to the head. 10, 20, 30, 40, 50. Now, think about this. If I'm always adding it to the beginning, to the head, what order should I expect out of this? If I add 10 to the head, right, and then I add 20 to the head, that's going to look like this. I add 30 to the head. 30 is going to be the new head. 40. Give myself some more room. And then finally what? 50. That's what it should look like. All right, let's come back over here and print it out. Is this going to work, by the way? What's this going to print? Blah, 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 right? The default Java virtual machine memory address. Back to the drawing board. One way that I could do this is I could fire up my debugger, right? Debug. And when I get to that point, what I could do is I could look at the list. I could expand it out, and I can see there's the head. Well, what's in the head? There's an element of value 50, and it has a reference to a next with a value of 40. That has a reference to the next with a value of 30. That has a reference to next, which is a value 20. And that has a value next, the element holding 10. And then finally, the next is null. I visualized my, my linked list here in the debugger. Right. So I'm convinced that it works, but that's not really convenient. I really do want to print this out so that somebody can look at it. Right. So let's go back to the drawing board. Stop the debugger. I'm convinced that it works, but I want some additional convenience here. Right? Let's go ahead and implement a toString method. In fact, I don't want to do it. I don't like working. Generate toString. Is it going to be smart enough to do this for me? my linked list head is equal to head. All right, that's all it's going to end up printing. Right. In fact, over here, it's still going to print this garbage here. This head is equal to a list node instead, a node, right, with a memory address. So let's actually go over to the node first, okay, and create a toString method here. Public string toString. The only thing I'm going to print here is this dot element dot toString. Return that toString method. Right? In fact, I'm not even going to go toString. I'm just going to go ahead and, well, I have to, I think. Yeah. There we go. I'll do it like that. It's going to fail if it's null, right? Because you can't call toString on a null element. So maybe I want to implement some more, logic here that if the element is null, then I will go ahead and print out the null. Otherwise, I'll go ahead and do this toString. I'll leave that as an exercise to you. Come over here to the demo, and at least it prints that 50 now. Right? That's not really what I want, though. Right? What I want is something that looks like that. Okay. That means I'm going to have to write it. Right? My IDE is not smart enough to do something like that. So ideas? Remember that this is the head. This is going to be my first traversal algorithm, right? And this is the tail. And remember that the tail points to null. So what I'm going to do is I'm going to start at the head, grab the string value of that element, then go on to the next one. Maybe concatenate an arrow here to make it look cool. Right? And then I'll get the string value of the next one. Keep going, keep going, keep going until what? There is no next element. Do I know up front how many elements are already in here? Nope. So what kind of loop does that suggest to you? A while loop. A while something, right? Now, that does seem like a design flaw. Right? I don't know how many elements are in this list. If you want to do anything index-based and throw an exception for an index out of bounds, right, then there's really no way except for traversing the entire list to find out that you've fallen off the edge of the earth or whatever. It's going to be a bunch of manual work. So maybe I'm going to write a note to myself here because we'll do it next time. To do. Support a size, int size property parameter, or not parameter, variable. Right. Okay. For now, I'll just go ahead and leave that as a to-do and we'll come back to it. What I want to finish up today here, though, is this print method. This is going to be our first traversal algorithm. I'm going to start at the head, and while there's still a node to traverse, I'm going to be concatenating a bunch of string values. Right? Well, I need a starting point. I will create a node, which is the current node. Right? Where should I start? Remember, loops are all the same. You have an initialization, a continuation, and then an increment towards your termination condition. So here, this is my initialization. Instead of int I equals 0, while I is less than 10, I plus plus, now I'm doing things in terms of nodes, in terms of objects. Right? I've got a current. Where should I start it? This dot head. Excellent. While, and I'll put it in English here, right? While the current node is pointing to a valid node, dot, dot, dot. Don't know where that A came from. Right? Then I will concatenate the string of the current node, right? Plus a, I don't know, this cool looking arrow. There we go. Right? And then go to the next node, dot, dot, dot. So I've got 3 things to write here. First of all, let's go ahead and create a string builder so that we can actually do this. String builder, SB is equal to new string builder. There we go. Right. How do I tell if the current node is a valid node? Again, visually, that's valid. Valid, 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 valid. Invalid. Right. So in other words, while the current node is not equal to null. We could do this in terms of has next, right? Does the current node have a next? No, then break out of the loop or something like that. This is going to be much cleaner though. Right? So while the current node is null, I will concatenate onto the string the current node value. And so that's going to be sb.append, what is it? Current dot get element. And that toString method will take care of that. Plus a neat, cool looking arrow thing. Right? There. Go to the next node. How do I go to the next node? I'll change my current to current is pointing to the next. Current dot next or get next. Right? And I'll simply update the current node. Right? Again, visually, what does that look like? I've got this reference to current. I initially started out as head. Well, and then I set it up so that the current's next is referring to this 40 here. So I'll update that to be the next. Next, next, next. And then finally, when it becomes null, we break out of that while loop and we're done. Okay? And then finally return sb.toString. Right, dump your string builder to an actual string and then return it. What does that look like now? Nice. Right? What about this thing right here? Again, what's better than good? Good enough. Right? So what you could do, of course, is you could use the has next to break out one iteration early and then take care of the last node outside the loop. Okay. All right. Well, we've got enough time. Do we want to go back and do the size right now? Okay. Int size. Make it private so that you can't change it. I'm not going to get rid of my to-do until it's done. And until it's to done. Right? What should I initialize it to? Well, how big is the list to start out with? 0. If I add an element successfully, what should I do? Size plus plus. Well, if you're going to implement it, you might as well give the outside world access to it. Public int get size. Return this dot size. Right. Now note here, this is not a leaky abstraction because it is a big I or a small I integer. I'm returning the value of it. It's still private. You can't change it from the outside world. Right? Okay. I could maybe incorporate that here. sb.append size equals plus this dot size plus, and then maybe a cool looking colon or something like that. Size is 5 and here are all the elements. Right. Okay. That's it. That's all you needed for the size. Because I kept track of it. What if I did not keep track of it? I'll keep it because I really like that design, because no fuss, no muss. But let's think about get size here. What if you didn't keep track of the size? Is there still a way to compute the size? Int size. I'll start it out at 0 and return size. How would I go about doing it? Here are 5 elements. There's the current node, plus 1, plus 2, 3, 4, 5. And done. How many elements are in there? 5. So in other words, exactly the same while loop here, but instead of appending a string to it, what would I do? Size plus plus, and then go on to the next node. Right. Note here, this is cruft. Do we remember what cruft is? Right. So Harvard or Yale or somebody have this cruft hall, right? So we are in Avery Hall, right? Maybe someday we'll abandon Avery. And one day they abandoned Cruft Hall, and it became a dumping ground for all their garbage, right? So you have a overhead projector and the light is blown out, or somebody cracked the screen or something. What do you do with it? Throw it over in Cruft Hall until the Cruft Hall became filled with garbage, and then they tore it down. I don't know what happened to Cruft Hall, or if they renovated it or something like that. But the colloquialism came to be known as cruft. Unneeded crap that you should just throw away, right? Don't save it. It's not gonna like somebody's going to fix an overhead projector, right? Get rid of it. This code is self-documenting, right? You do not need to document each one of those steps. I did so as a demonstration of here's what we need to do. 1, 2, 3. You go in, you fill your code in, and then you get rid of your comments. Right? That's a very common, outlining your code. Right? It goes all the way back to the technical writing that we were talking about earlier in the semester. You have a draft, right? Here's step 1, step 2, step 3. You fill it in, you get rid of that cruft. Right? This dot size, dot get size. There we go. That fixes that. And I believe that we'll have the exact same. Yep, size is still 5. What if I were to take something out? What would I need to do then? I would need to come back and, of course, re-support this here and size minus minus. Right. Let's think about these two designs, though. Every time you add something, you increment this counter. Every time you remove something, you decrement that counter. Versus recomputing it every single time you want the size. Which do you think is more expensive? Recomputing it, right? Because why? Suppose that there are 1 billion elements in there, right? And I just want to know how many elements are in there because I want to make sure that I stay within bounds and ask for only valid elements. Every time you need to go through and count to 1 billion. Okay, 1, 2, 3, 4, 5, 6, 7, billion, right? Here you go, billion, right? You ask for that again. Okay, well, I'll do my counting again. 1 billion elements, 1 billion elements, 1 billion elements. That gets quite to be, inefficient. Right? I'm going to show you right now as a, since we have time, just how inefficient that is. Right? So I'll simulate adding elements random r equals new random. Simulate adding elements as long as the size is less than 1 million. Right? So while my list is .get size is less than 1 million, 1, 2, 3, 1, 2, 3. List.add, they're add an element to the head, and it's going to be r.nextInt. There we go. So as long as I've not hit that 1 million, right, I'm going to go ahead and add another element, add another element, add another element. When it gets to 1 million, I'll stop, and instead of printing the list because it will be unwieldy, I'll put done. Okay. How long should we wait? Well, we only have 7 minutes technically left. Let me go ahead and kill it. Should it take that long to add 1 million random elements? Right. For int I equals 0, I is less than 1, 1, 2, 3, 1, 2, 3, I plus plus. List.add element to the head, r.nextInt. Right. Get rid of this. All right, now pull out your stopwatches. Done. All right, nothing. All right. That was the cost of adding 1 million elements. It should have been instantaneous. All right. But checking that size, every time you do it, that's going to lead to 1 million times 1 million. What do we call them? All right, so there's this old movie. I always like to quote this old movie. Once Upon a Time in the Old West. Right? So it's an old Western, and of course, money, inflation and stuff. They were talking about that land must be worth hundreds of thousands of dollars or thousands of dollars. And then he says, "Yep, they call them millions." Right? So what is a million? It's a trillion, right? We call them trillions, right? 1 trillion operations. I've got an i9, right? It's single-threaded, and OBS is running, so it is running at a disadvantage here. But it shouldn't take this long at all. No, right? So efficiency, we're going to start getting into that. Does that necessarily mean a linked list is bad? No. The design currently is bad. what we're going to look at once we're done with our linked list implementation is that linked lists are good as in efficient in some situations and inefficient in other situations. Whereas an array-based list is efficient in the opposite situations, and then it becomes inefficient in the other situations, right? And this is why you need a variety of data structures. And you need to be able to understand when and where to use the proper data structure. Okay? This will not execute within a few hours, I guarantee it. All right. Got a lot of questions answered today about fictional characters' names after numbers, right? If nothing else.